26? I think we were on 40.
We were on significant figures.
No, we were on using scientific measurements. We were on 44. Because I remember this like dartboard thing.
I do not. But okay.
Yep, we were on the dartboard. Okay, so we were talking about accuracy and precision in measurements. The big idea here is measurements and making sure that we are not reporting a measurement that's more accurate than the tool that we're using, right? Okay. So whether it's a ruler, graduated cylinder, balance, we want to make sure that we don't do that. Think about your electronic balances. Okay, it measures in grams, and do you remember how many places it will measure to?
Like the tenths, I think. Is that
Tenths or hundreds?
hundreds?
Hundreds, right? So it'll measure 2 places. Okay, and then our balances are like, I think our balances are like 1 kilogram balances. So you can measure up to 1 kilogram, which is 1,000 grams. So that's it. Like that's as much as you can measure. So on that balance, those are as many digits as that thing is going to show you. Okay. So on this first one, 11.09. So the balance is telling us that there's a 10, a 1, no tenths, but almost a tenth, right?
Yeah, almost.
0.09, so it's almost a tenth. Okay. If you were to put just something very, very tiny on there, would the balance change?
What do you mean?
Like if I just put a little fleck of dust on there, would it change? If the little fleck of dust was
Weighed like 100.
at least that, right? But what if the fleck of dust was like,
Then no, it wouldn't change. Unless,
how many flecks of dust would I have to put on there before it finally adds up to get to the place where it's like, oh, that's a 100?
a few.
A few, right? Okay. So when we talk about significant figures, that's kind of the idea that we're going to get to is like, how do we estimate between the spaces between the lines, like on a ruler or a graduated cylinder? And then that gets to another idea here, okay? About what are our digits doing on the number line, okay? In that balance, the balance is telling us that these are the values for those places, okay? We can relate this to the metric system because when the decimal place is in that it's the 0 spot. When the decimal point is in its base location, what is the value of the first place? 1. What is the value of the second place? 10. Third place? 100. Right. So when the decimal point is in its base location, we know what those values are. The metric system, using a metric prefix, allows us to change what the base means. Right? So if we put kilo in front of that, now what's the value of the first place?
In kilos, I don't remember. A lot.
A lot. Yeah, just flip back. What does kilo mean?
Kilograms.
Back on
The
35.
unit of mass equal to the mass of the initial prototype of kilogram.
Back on 35.
Yeah, I'm on 35.
Yeah, that table, what does kilo mean?
Oh, 10 to the third.
10 to the third, which is 1,000, right?
Okay.
So by putting kilo in front of our unit, that changes the value of the first place to 1,000. So if I write 1.0 kilogram, right, that's 1,000 grams.
Why can't we all just use the same, like, unit of measure? Or, like, not
that's what we do, that's what we do.
They need to make it complicated.
Alright, so, the graduated cylinder problem, gives us another perspective on like what are our digits mean. So, in the flask, what did we say the volume of that would be?
I don't know, I can't see.
We decided it was, what did we decide?
360?
360, so the volume
360 milliliters, right?
was 360.
360. Okay. So we decided it was like 360. Okay. When we look at that number, oh no, not 360, 260.
I was gonna say 50.
260. Okay. If we look at our digits, are we measuring 200 milliliters?
Yes.
Yes, we are measuring that. There's a line that means 200, so we are measuring
Right.
at least 200 milliliters. Are we measuring 60 milliliters?
Yes.
Is there a line that
Oh.
says, are there lines that mean tens of milliliters?
No, but that one right there is 50.
Okay, so we know that one's 50, so there's one line that means 50.
So it's above 50.
So the only thing we know is it's above 50.
Yes.
How much above 50,
We don't know.
we don't know.
It was just like an educated guess.
Just an educated guess. Right, we're probably pretty sure, we're sure enough that we can put that 0 on there. But why do we have to put the 0 on there? Okay, so think about that. Think
Because
about that
otherwise it
question.
would only be 26.
Okay, good. So let's look at the graduated cylinder. So in the graduated cylinder, here it is. All right, the graduated cylinder. It's like there's 8, and then there's a line, and like the liquid level is like right on the line. So there's 8. And then the line, so then we have to look at the lines. The lines mean, do the lines mean 1 or something? No, the lines mean something less than 1 because the next big line is 9. And so there's 8, 1, 2, 3, 4, so each line means 0.2.
0.2.
0.2. So, and the liquid level is like right on the second line. So that's like 0.4, so it's gonna be like 8.4. Okay, and since it's right on the line,
Then we know.
so we're measuring this one.
Yeah.
We're measuring this one, because there's a line that says 0.4. And it's right on the line. What, could we say 40?
Yeah. Well, no, because that's more accurate than. Well, we could say 40.
Well, we know it's 8, we know it's 4, it's right on the line.
So we could put 0.
We could put a 0. We're not sure. I mean, we're sure that it's right on the line, but are we communicating something more than what the graduated cylinder is telling us?
No.
No. Right, it's right on the line. Okay. So, here's the scenario. If I were to take these 8.40 milliliters of liquid and pour them into the 260 milliliter flask, how much water would I know I would have in the flask?
Like 8.
Would I have 268.40 milliliters?
No, you probably have like 268-ish. You probably have like 268. It would probably be a little bit under. Well, we wouldn't know. We wouldn't know.
Because how sure are we that it's
60. Yeah, we're not that sure.
So
Right.
it could be a little more or less.
So, I mean, we're sure that the graduated cylinder has 8.4, but here's the idea. If we pour that into the flask and then we use the flask to measure, What's the flask gonna tell us? Well, at best, what's the flask gonna tell us?
8. Maybe.
Maybe. Right? Would I, on the flask, would I know the difference between 60 and 70?
Yeah. No, well, no, because there's not a line. There's only a line for 50 and
There's only one
300.
for 50. And so to know the difference between 60 and 70 is like,
This is hard.
no, well, it is hard, but it's gonna illustrate something important. And we already kind of alluded to it. Okay. So, since, like when we try to decide what our answer is gonna be, okay? Our flask cannot measure tenths, so we've had to drop those digits. Okay. Did our flask measure ones?
No.
No. So we have to drop that digit. Okay. So, since we dropped this digit and it's an 8, what do we do with this
Round.
digit? Round it to,
7.
so
It'll say about 270.
Okay.
The flask.
and if we actually did that, okay, we might eyeball that at 270, okay? Well, let's use this. So our number, okay, was 268.40. I had to drop this and this and this, so then is my number 26?
No, it's 27.
Oh, no, is my number 27?
No, because you have to have 0, 0 still.
So is it my number 27?
270, not 27. 200. You have to add a 0.
I have to add in a 0, so, okay. Because it's not 27 point, is it?
No.
And so to show that the amount in the flask is at least 200, what is the role of my 0?
To tell them that it's not 27, it's 200.
Right. It's to placeholder, right? It's to push the 2 to the 200 spot.
Fire.
Feel pretty confident with that?
Mm.
What about this 0? What's the role of this 0?
To be the placeholder for the 9.
Is it just the placeholder
No.
or did I actually measure that?
Well, you have to measure that.
I mean, the balance actually measured it. It's like, there aren't any. Let's go to the next place. How many are there? 9.
Almost. There was almost 1.
So in this case, the 0 is actually doing something. I mean, the balance says there aren't any of them, so let's move on. How many are there? Okay. Same thing, and we kind of guessed at the role of the 0 here, that that's just a placeholder. It's making it say that it has 200. Okay. What about the 0 here? What's that telling us?
It's telling us that it's on the line.
Right, it's telling us that as best as we could tell, there were none of those. It's right on the line, so we're actually measuring.
Yeah, Lucky?
Sometimes in math, we write numbers like this, 0.10. What is the role of that 0?
So you know there's a point there, so you don't think it's 10, you know it's 0.10.
Okay, so that kind of just identifies the place of the decimal point?
Yeah.
Okay. This is not really.
No.
If we wrote it like this, does that
Same
change
thing.
the meaning of the number?
Okay.
Alright. Good. We have basically just summarized significant figure rules. Okay. Because if I have a digit, what do I have to do with it?
What do you mean?
Like if I have a non-zero digit, like if I have a 1,
Yeah,
or a 2, or a 3, like what do I have to do to it?
you have to write it down.
I have to write it down.
Put it there.
As part of my measurement, I gotta write it down. Zeros, though, what we see here is zeros do different things depending on
Where it is.
where it is. Okay, so let's flip over to 46, and we're gonna read about significant figures. Okay, and so, does anybody wanna volunteer for that paragraph on significant figures?
I will.
Okay.
In science, measured values are imported in terms of significant figures. Significant figures in a measure constant of all the digits known with certainty plus one final digit, which is somewhat uncertain or is estimated. For example, in the reported nail length of 6.36 centimeters discussed above, the last digit 6 is uncertain. All the digits, including the uncertain one, are significant, however. All contain information and are included in the reported value. Thus, the term significant does not mean certain. In any correctly reported measured value, the final digit is significant but not certain. Insignificant digits are never reported. As a chemistry student, you will need to use and recognize significant figures when you work with measured quantities and report your results, and when you evaluate measurements reported by others.
Okay. So, significant figures. Some of them are certain. Some of them are uncertain. We already established that. And we don't ever want to, how many uncertain ones do we want to include?
One.
That's all we want to do. Okay. Noah, you want to do that next paragraph?
When you look at a measured quantity, you need to determine which digits are significant. That process is very easy if the number has no zeros, because all the digits shown are significant. For example, if you see a number reported as 3.95, all three digits are significant. The significance of zeros and number depends on the location, however. You need to learn to follow several rules around zeros. After you understand the rules in table 2 defined, using to express the answers in the sample column that follows.
Okay. So in your notebook, here's what I would just do this. Write a couple numbers following the example on 47, and then we'll be like, oh, this is significant, why? This is not significant, why? So the first rule is that zeros appearing between digits are significant. We saw that here. So when a zero is in a number between two non-zero digits, that's significant. Okay, the next rule, zeros appearing in front of non-zero digits are not significant. Okay, so we'll need to talk about why. 0.09.
Oh my gosh, I'm actually tweeting. I just spelled front F-O-R-O-U-N-T.
Forum?
F-R-O-N-T.
Okay, so if we were to look at these two numbers, this one only has one significant digit because these zeros in front are not. Okay? This one, again, only has one. So, why? The basic reason is these zeros are doing the same thing as this zero.
But aren't they showing you where the, because if you didn't have those zeros, then it would just be 0.9, and 0.9 is different from 0.0009.
Correct. Okay. But they're really just identifying the
Oh,
place
they're
of
just
the
identifying.
decimal point. Okay. And I think, one thing that I use to kind of help rationalize this, how would I write this in scientific notation?
Oh, scientific notation. Oh my gosh.
Right, scientific notation takes care of all the zeros to move the number, or to move the non-zero in front of the decimal point.
So what
Right?
would
So
that be? We would use,
so this would be 9 times 10, right? Since my number is this side of the decimal point, my exponent's gonna be negative.
So it'll be in millimeters. No,
Right.
micro. It'll be micro.
Okay, good. It's interesting that you did that. Okay. So when I write this in scientific notation, all those zeros go away and this becomes 9 times 10 to the negative 4th.
But, or,
So
you could do this though, right?
you could, and I'll, since you brought it up, I'll show you. So how many digits do I have? One. I'm gonna have one. Because scientific notation takes care of all the zeros. So, Ally brings up an interesting thing.
It would be in milli. because-
Go back to 35. Okay. And notice that all of our abbreviations have exponent factors meanings.
Yeah.
Okay. So let me do a different one. Okay. This number,
So that would be in micro.
what is it?
Oh,
I mean, if we're, let's just say this is.
what is
Scientific notation. 1, 2, 3, 4, 5, 6. 9 times 10 to the negative 6. All of our metric prefixes have exponent definitions. Well, what is the definition of 10 to the negative 6?
micro?
Micro. Okay. So these two things, they like mean the same thing.
So you could put 9 micro, but what would it be? Micromillimeters, microcentimeters,
No, meter.
micrometer.
So whatever unit we're measuring, whether this was grams, meters, or liters, right? Then we would just say that this is 9 micrometers.
Even if it was in liters, it wouldn't be microliters.
Then we would say 9
Micro-
micrometers, or 9 micrograms, whatever it is. Right? But that is telling us that. So if I needed to do a quick metric conversion, which we're going to be using this strategy later, we can very, very quickly do the metric conversion because we know what it means. So the exponent value and the abbreviation we can substitute.
Fire.
This is what makes the metric system like pretty slick, really. I mean, people were pretty smart when they put it together. They were thinking about it.
They were thinking about it.
Okay. So, right, when we put 9 on the number line, and we've defined this as micro, then what does the first place mean?
It would like to the
1 millionth?
1 millionth?
So
Something
this
like
is
that.
9 1/millionths. Because we use that to change what the first place means.
Okay, I'm kind of catching on.
Which is why these are not important zeros. This is gonna be very handy. You know, why do we use scientific notation? To deal with really, really big and really, really small numbers. And so the metric system becomes very useful when we start doing that. Okay.
That makes sense.
Alright, rule number 3. Zeros at the end of a number and to the right are significant. So if we do something like this, 85.00, okay, these,
At the end to the right,
yep, so something like this, so it's to the right of the decimal and on the end, okay, those are important, and think about it. Why would we have written them?
To like show that it's on the line, like it's,
to show that we actually measured them and there were none of them. Okay? So we're showing that. Similarly, yeah, 9 point, a lot of zeros. Right, how many of those are significant?
the first, no, none of them, none of them. All of them?
All of them.
Oh,
Because we measured, because we
Oh.
looked at our tool and our tool told us that there were none of them. None. There's a lot of nothing.
Do you really have to write all of those zeros?
Well, if you measured them, you should write it. But like our electronic balances, how many places are our electronic balances measured?
100.
Just right. Even the really, I mean, like what we would get in school probably is only going to be 4 places. Right.
Do
This
they
is-
have things that measure that much?
So they have, and we'll watch a video on using like a laser to measure distance. And because you're using light to measure distance, I mean, you can measure a lot of places. So that you get a very, very, very accurate measurement of distance using a laser. Okay? All right, last rule. The last rule is zeros at the end of a number, but to the left, are not significant, okay? And we saw that here. So in a number like this, in a number like 260, this one is not significant. We talked about why. What is that zero doing? What's that zero doing there?
It's just being a placeholder.
Just a placeholder, making that 2 be in the spot it's supposed to be.
Yeah.
Now there is a exception to that rule. Like, what if we actually did measure it and there were no ones? How would we show that the zero is significant?
By putting a point after it?
By putting the decimal point after it. That tells us we did actually measure it and there were no ones, but that's as far as we measured. And so,
So you just have to put a decimal point for the most?
yeah, so you just put the decimal point, which makes the zero.
Important.
We actually measured. So 260 would have 2 digits, 260 point would have 3 digits.
So,
Okay, questions on that? How do we feel about that?
That's making sense to me.
Alright, so looking at those sample problems, Layla, there in sample problems 2-4, number 1, 28.6, how many digits are significant?
In
oh,
Page 47, 28.6.
3.
3, good. Noah, 3,440. 4. Allie, 910.
no, just 2.
Just 2 of them.
Just 2.
Layla, 0.04604.
Ouch.
Yes. Be confident. 4.
Okay.
Noah, 0.0067000. 5. Yeah. Very good.
Wait. 1, 2, 3, 4, 5. Okay, yeah, that makes sense.
I mean, some books will use, well, okay, and it's kind of an interesting thing. And I think textbooks do different things depending. Numbers, like if this number, like with this, 1, 2, 3, 4, 5, 6, 7, 8, 9. Out in front of the decimal, they use commas to break it apart, and then nothing. I've never gotten that.
No breaking it up. Because they don't
I don't
care
know.
about them that much.
Some textbooks, like this one,
We'll just put
they just use basic.
Yeah.
That's right.
Yeah. I'm sitting down for too long. You're sitting down.
Oh, your hips.
Yeah.
Alright, the last thing, because this will go quick because we've already done it in the problems, and we see how it is. Okay. So, when we add and subtract values, okay, so now we know that we take measurements, and when we take measurements, some are significant or uncertain, some are not. Adding and subtracting. So now we're on page 49. When adding or subtracting decimals, the answer must have the same number of digits to the right of the decimal point as there are in the measurement, having the fewest digits to the right of the decimal point. So, given something like this, 5.44 minus 2.6103. When we add and subtract, we're just concerned about how accurate it is after the decimal point. Okay? So, this one has 2 places after the decimal, this one has 4 places after the decimal. When we do our answer, we can only show 2 places after the decimal. So then that's gonna
Will we round?
make the
or
question, then what do we
just-
do with the other digits? So then we'll have to round, alright? So, kind of like what we did when we added it up, when we added this, like when we added the graduated cylinder to the flask, right, that's the scenario. So, we add this up, it's 0, 3, 5, 10, 8. Okay, so it's 8.0503.
So it's just 8.05.
I have to drop this digit, I have to drop that one, because that's 0, what do I do with 5?
You do nothing.
Nothing.
Just stays.
So 8. Okay. Let's do this one. We'll change this to 5.44 plus 5.0892. Okay, we add this up. 2, 9. Oh, I shouldn't have done that. But 9, 4. Okay. So I add that up. I have to drop this digit and this digit. I have, because I dropped this digit, what do I have to do to the 9?
Round.
Round it up to
10.
10.
That's gonna be, so it'll be 10.50.
Yes, and I want to include the 0. Okay, so 10.50. When I round it up. Okay?
What's the difference between having a 5 there and having an 8 there?
It would have been 12. I guess you're right. I was overthinking it.
Okay. Me too, then.
If it would have been a 2, then right, that just would have been a 3. So. We get the idea.
We get the idea.
Okay, so addition, subtraction, we're just looking at how accurate it is after the decimal. The one with the least accurate is is our guide to how many we put in our answer. Okay? Alright. Multiplication and division. Oh, there it is, okay. So multiplication and division, here we actually count how many we have, and our answer can't have more than the least. So, what does that look like? take 85 times 43. Who's got a calculator? I don't need that.
I don't.
Oh, I bet it's my phone.
Is it out? Perfect, it's out.
Plugged
Use it.
in. Perfect, it's out, use it.
Use it. $3,655.
55?
Yeah.
Okay, so, maybe this was 85 centimeters times 43 seconds. So this 85, how many significant digits? 43? 2, okay. So then our answer can only have how many significant digits?
Oh, wait,
So,
what? Why?
That's weird.
it is.
Because now, so how are we, so basically we just have to chop off the 5s, make, that a 7, and then put 2 zeros.
Because
It can't just be
it
36.
can't just be 36, we have to say it's 3,000, so we have to have 2 zeros as placeholders.
Yeah.
And so this becomes 3,700, and our units are centimeters per second.
Oh, cool.
I think the reason why multiplication and division are different is because, like in a multiplication operation, right? You are like, your decimal place is moving, or you know, the magnitude of your change is a lot bigger, right? We went from 85 to 3,000. We went from 80 to 3,000. So it's just, there's so much more change. So. Okay. Similarly in division, so let's do 85 divided by 43. $1.97674418. Good.
6.
And I think this will illustrate it. Do 43 divided by 85. I'd go like a book.
0.5058.
50, 50. If we use the same rule as addition and subtraction, do we have any digits after our decimal point?
No.
But now, like, all of our digits are after the decimal point. Because when we divide, we can end up with numbers less than 1. So it's like, well, we have to have a different rule. So, we count these up. This one has 2, this one has 2. So this can only have 2, so we drop the 7, we drop the 6, we drop the 7.
But we round up, so it's gonna be 2.
2.
0.0.
0.0. Okay. Same thing here. We're going to drop the 8. We're going to drop the 5. And now this becomes
0.51. Fire.
I think we're ready. We can take a quiz.
Yeah, let's do it. Do we get notes? I'm joking.
Boom. Questions on any of that?
No.
I'm ready to take it.
Boom. That was like 2 days on chapter 2 with that. Let me ask you a couple questions.
Okay, I'm ready.
So, when we do our metric conversions, we're really going to focus on a few of them. We're not going to focus on a lot of them. So,
Can I use page 35 for this?
yeah, and I'll print. I have to remake my poster, and I'll print out a poster that I'll use. Actually, I might have it. And then you can just use it as like,
There.
it's not a huge thing. So we'll probably go like mega, we'll probably use mega and kilo. So mega and kilo. But then we won't use those two, and then we have our base unit, our base location. Which was B, because I don't think there's any B's. And then we won't use
DC,
-1 deci.
deci,
We don't really use that one.
but
We use centi and milli a lot. And then we'll use, and I better make that look like it's a lowercase. And we'll use micro, which is the funky
upside down.
upside down and backwards YU thing.
Why?
Okay, so mega is 10 to the 6th.
Yep. Kilo is 10 to the 3rd.
Our base unit is 10 to the 0. Here's a challenge, math challenge for you. Why is 10 to the 0 1?
Because it's 10 times, well, I don't know.
No.
Centi is 10 to the -2.
Milli is 10 to the -3, and micro is 10 to the -6.
When we get into the light unit, we'll work down into nano, so 10 to the -9. And then we'll learn
Wait,
another
why
one.
is 10 to the
Because 10 to the 1, right? 10 to the 1 means,
10 times itself?
no, because 10 times itself would be 100.
Yeah.
10 to the 2 is obvious because I have 2 tens.
Yeah.
Oh, okay. Well, 10 to the 1 should be clear. It's like, oh, I have 1 10.
So 10 to the 0, why is that 1? Because there's nothing.
No, there's not nothing. There's 1.
Right, but if it's following your 2-1 logic, then it would just be nothing.
Which would be 0, but it's not.
But it's
And
not,
zero's
it's
not.
1. So why?
Yeah, that
Tell
makes sense in my mind.
Wrap your math brain around that one.
So my math brain's not that
struggled
big, it
in
doesn't
math,
read.
Okay, so, and kind of back to this, right? It's just telling us what that first place is going to be based on our exponent value. So, if we're going to convert, 1,000 meters to kilometers, then we are at our base unit.
Is meters 0?
Yeah, meters, so meters, liters, grams, they would be 0.
Okay.
And so we're moving from 0 to
Okay, so
10 to the 3rd,
10
to
the
3,
3rd. So what's the number? 1,000?
1,000.
So it would be just 1.
It would just be 1, right? So we're moving from 0 to 3. And that, so what does that tell? That just tell us that we're moving our decimal 3 places.
Yeah, exactly.
Okay, or we're moving our decimal that direction. Okay. I like to think of it this way because I never could oh, you moved the decimal place to the right 3 places. I'm like, no, yeah, what does that mean?
What is that?
To me, it was always better to say, all right, if I'm moving this way, it's easier for me to think that my number is getting smaller.
Yeah, well it is.
When I go to a bigger unit, my number gets smaller. So bigger to bigger gets smaller. So 1,000 from 0 to 3, since I'm going to a bigger unit,
It's small.
by the number of places that that's great. So then really I only have to remember one rule, because then if I'm moving the other direction, then the opposite,
So to get smaller, it gets bigger.
right? To smaller
Gets
gets
bigger.
bigger. Okay. So if I had 1 meter, how many millimeters? number's gonna get bigger by 3 places.
Oh, 1,000. Oh, cause the point is after the one.
Okay, alright, let's try something not straightforward.
Oh,
Not straightforward.
I'm not good at that, screw it.
48.63 meters is how many centimeters?
It's gonna move 2 places.
And my number, because since I'm moving to something small,
It'll get bigger, so it's gonna be 4,863. Yeah, you got it. Fire!
just remember the rule.
Just remember the rule.
Okay. Allie, have you taken anything from
Okay,
You don't
point 8651 kilometers is how many meters? So kilometer to meter
Kilometer
is
wait,
3 places.
kilometer is our baseline, right?
No, meters are basically. So we're moving from
Wait, where's kilometer?
10 to the 3.
Oh, kilo.
Kilo. So we're moving from kilo to,
2, so it's gonna be getting bigger by
So,
is kilo something big or something small?
something big.
Something big to something small.
So the number's gonna be getting bigger.
Yep, so we're going to a smaller unit, so our number gets bigger.
So it'll be 86 point, no, it'll be 865.1.
There you
Oh,
go.
0.16, I had to
865.
I thought that was a K.
Oh, no, 0.1, that is a K.
Oh,
that is a
thank you.
K?
Sorry, my K is,
That looked like a 6.
I'm,
That
I-
was
I'm
a
used
6.
to, I'm used to your K's looking at like that, so I was like, I thought that was a K.
so 865, right, 3 places, 1, 2, 3 to make our number bigger.
Oh, okay.
So, if I do this,
I can't see what you-
86.51 kilometers
Is
to
that to
megameters.
megameters?
Megameters.
So that only goes up 1, so it just gets smaller by 1.
No. Kilo is 3, mega is 6.
Oh,
So there's
you're
no,
right.
there's no names for 4 and 5.
So it just gets smaller by 6, or by 3, 4, 5, by 3.
By 3.
It
The
just gets
distance
smaller.
between here is 3, so it gets
So
bigger.
So it's gonna be 0.08651. Oh,
No, because you have to round.
because it's going back 3. 1, 2, 3. 1, 2, 3. So it's gonna be 0.08651. Yeah, we're right.
Oh.
Why were you side-eyeing? Why were you side-eyeing?
I just want you to be sure.
I was sure, but you were.
Allie
like-
was sure. I think he was trying to make sure
Well,
I
then you
was
could
sure.
just be like, don't side eye me, I know what I mean.
Stop making faces at me. Noah hasn't said anything.
He hates this nonsense. He wants to get around chemistry.
Noah doesn't want to be here anymore.
I don't think that's true. I think there's words in it now. That's not true.
Yeah.
Alright, okay, so metric conversion. So I'll either leave this on the board or I'll make a post. I have a poster, I just can't find it.
That's a good poster.
That's a great poster.
You should make a poster that looks like that.
Well, I have one, I just gotta find it.
Oh.
I may have,
Figure out
to
where it went.
I may have to reprint it out.
I can laminate it for you. in
I
Mrs.
could
Williams.
also laminate it for you because I know how to do that. I just need to find the
Okay.
key.
So,
I don't know where the key is.
measurements.
It's everywhere on her desk. It's not there.
Metric conversions. Our lab Monday, no, our lab on Tuesday, will be going through measurements,
Okay.
and using different glassware and looking at the accuracy of different glassware. And
Okay.
Well,
We're
the
gonna-
flask is not it.
The
Is what
flask
we've
is not
decided.
it.
okay. So questions on any of that?
No.
You really have a struggle bus.
Dude, like, it's not even that they hurt, they're just sore no matter what I do. Like, usually when your arms are sore,